on live. Yes. And we are back live. Wonderful once again. Absolutely. Okay. So Wednesday, I was proctoring an AP test. But you already heard my rant yesterday. That was fun for me. I don't know. So, Nicole, you were in class literally right at this time. I was standing still for 20 minutes outside of a trailer next to the Collins School, waiting for someone to come over and unlock the door so I could take the kids in so we could start taking the test. Hilarious. You would think, like, oh, all this planning into AP testing. Oops, who's going to unlock the door? No one. So, it was hilarious. But at the very least, it was a short day for me. I was basically home by noon, and that was fun. But you guys had a half day anyway, so whatever. Okay. So, Wednesday. I'm sure you saw the assignment. You weren't here, but you saw the assignment. That assignment, just to clarify, is not due until Monday. It's not due until Monday. There were two portions of it. There was a research portion and there was a coloring portion. Nicole, I did get the copy of your coloring thing that the sub left in my paperwork. So I do have that. Basically, Patrick, for you guys that were here, I made copies of it and I said, hey, use my colored pencils if you want on Wednesday. But then the research, of course, you could do as well because it was only like an hour class period. So I can get you those copies, the printed out copies for the people that are online. Unfortunately, for that assignment, and just for the record, the name of the assignment was the 4-color project / absent day. If you're online, then I can't print them out for you. You'll have to print it out yourself or use technology to color that thing in. So, but yeah, all the information is there. Part of my goal for today is for the last 25 minutes or so, give or take. I haven't decided yet. I want to give you guys some more time to research for that project. It's not due till Monday, but I wanted to make sure that I gave you a little bit of class time to do that. So in the last 25-ish minutes, which would take us boom, boom, about 8:15-ish. Around 8:15-ish, 8:20-ish, I plan on basically calling an end for the live stream at that point, and basically saying, hey guys, let's go work on our projects, and you'll have the time to do that. Actually, I'll probably keep the live stream up in case you have any questions at that point. But yeah, that's what I'll do for the last 25 so minutes. As for today, I do plan on continuing a little bit more with Pascal's triangle, just a little bit more with Pascal's triangle, and I plan on taking a step towards Fibonacci. You'll see what I mean when we actually get to Fibonacci. So, what I'm going to ask of you, now for those of you in the live chat, I can see you, the three of you so far. If you haven't left a comment in the live chat, please make sure that you do so. But if you do not already have them out, I'm going to need those notebooks out and open. Yes. Let's remind us of what Pascal's triangle was and how in the world it relates to what we are going to be doing with it next. Let me clear that out. Bring this up. Chapow, chapow, papow. Excellent. Zooming out. I have a book that I wanted to show you guys that I left on my desk at home, so I'm going to have to bring that in on Tuesday. But no worries. How good is this marker? This marker might be better. We'll see. Hold on, let me check. Yeah, that one's better. Oh, let's get rid of this one. Yeah. I missed it. Okay. Today is the 7th. Excellent. And I'm going to call this Pascal with a little arrow to Fibonacci. I got to double check if I think I spelled Fibonacci correct. Yeah. Where do you know Fibonacci from? taught you the Fibonacci sequence?
I think my 6th or 7th grade math teacher.
Did they tell you about the ratio?
I'm not sure, they might have.
The golden ratio, the divine proportion. We'll talk. We'll talk. That's my end game. First of all, Pascal's triangle. I'm going to replicate Pascal's triangle in its original form very, very carefully, but I'm not going to go like, yeah, I'm going to fill most of the page here. 1, 1, 1, 1, 2, 1. Did they tell you what Fibonacci sequence, like what it applies to? Okay. So you just like learned Fibonacci sequence and that's it?
I think so.
What kind of world is that? That makes them sad. So again, Pascal's triangle, just a very simple kind of adding game. The idea is that each row, ones go down the side, and when you have two numbers that occur on a diagonal, you can add them together. I'll just go down to this row right here. There we go. And it goes down infinitely. It goes down infinitely. This is just a little, I was just testing out my marker down there. But it goes down infinitely. Now, Pascal created this triangle. He knew some of the applications of this triangle. He knew of the connection to the binomial theorem, which I will write a little bit about that and its connections in a little bit. He knew its connections to combinations and thus probability. He knew its connections to that. He didn't know of the triangle's connections to other number systems like binary and trinary and the images that he could potentially create with this thing. It's absolutely insane. But this Pascal's triangle has many, many, many more applications than Pascal ever imagined. It's a simple triangle, yet it applies to number theory, it applies to algebra, it applies to probability and statistics. It's absolutely insane. And what I want to show you is how this particular triangle relates to the Fibonacci sequence. Now, the Fibonacci sequence, I mean, do you remember what the Fibonacci sequence was? Okay, that's fine, that's fine, that's fine. Now, the purpose is not to just stay with the Fibonacci sequence. The purpose is to take this a bit farther into the annals of mathematics. See, the thing is, like, the secrets of the universe are literally at our fingertips. It's just a matter of understanding how to unlock it. So this is Pascal's triangle, and we've been doing a bunch of stuff with Pascal's triangle. Let me use this. Now, you don't have to use a color. I'm using this mainly for the people online so that they can see this a little bit better, but check this junk out. What I'm about to do is I am about to draw some diagonals. I'm going to draw some diagonals on Pascal's triangle. And as I'm drawing these diagonals, now notice the angle at which the pencil is holding. Any number that appears on the diagonal, I am going to add up. Now, bring that thing down a little bit. There we go. Good, right there. That would be the next one right there. So let me actually get out another colored pencil. Purple one. That'd be good. So I'll start at the top right here. At the top right here, I'm going to draw a diagonal. It's going to look like this. And I get a 1. Oh, that diagonal's not showing up that well. Hold on. I'll do the diagonal a little bit darker for those that can see it online. There's the diagonal. And the only number that appears on it is a 1. So I just get 1. Cool. Here's the next diagonal. A parallel diagonal. And once again, you just get a 1. Great. Now this is where things start to get a little bit interesting. On this diagonal, You add the two numbers that appear on that diagonal, and you get a 2. On this diagonal, 1 plus 2 will get you 3. On this diagonal, I had to go down a little bit farther because the numbers were getting larger. But it's a parallel diagonal. And on this diagonal, I add up the numbers 1, 3, and 1. And I get a 5. Now, the numbers that I wrote in purple, do you remember how to construct the Fibonacci sequence?
Yeah, it was like 1 plus 1, 2, 1 plus 2, 3,
Exactly. Now, we'll come back to that in a little bit. But let me get the next number right here. If I add up this diagonal right here, 1 plus 4 plus 3 ends up being an 8. And then one more, last one that I'll do because I ran out of space for Pascal's triangle. But on this diagonal right here, 1 plus 5 plus 6 plus 1 gets you 13. Now, this thing would continue forever. And if you keep going on these diagonals, you create these purple numbers off to the side. Now, I keep mentioning the Fibonacci sequence. Obviously, Patrick, you alluded to the fact that you've been taught something of the Fibonacci sequence in the past. At this moment, I have not revealed how important this sequence actually is. But this sequence of numbers in the top right, that 1, 1, 2, 3, 5, 8, 13, which show up. Hold on, there's an announcement.
Isabel Kilmer and Val Amaro, please report to the auditorium. Isabel Kilmer and Val Amaro, please report to the auditorium. Thank you.
This Fibonacci sequence, which seems just not necessarily random for the lack of a better term, it just kind of comes out of nowhere. This sequence holds so much detail in how important numbers are to this universe. This sequence, which has a very specific rule to it, comes out naturally out of Pascal's triangle. There's a direct connection between Pascal's triangle and what we call the Fibonacci sequence. Even though Pascal and Fibonacci, neither of them knew of each other at the time, and neither of them knew that their two claims to fame were directly related. Pascal had no idea that this triangle could produce the Fibonacci sequence. Fibonacci had no idea that it was hidden within someone else's work. Yet there it is. This sequence of numbers is basically the cornerstone of the universe, believe it or not. Prime numbers are important, but the Fibonacci sequence has proved more important. Goodness. If I were to ask people, what's your favorite number? People would have a bunch of different answers. Most people would pick sports jersey numbers or something like that. I don't know. Some people would pick 7 or something like that. 13. I know it's unlucky, but it's my favorite number or some junk like that. I don't know. People have do you guys have favorite numbers? I have one. It's 17. I don't know why. It just is. Okay, that's fine. You don't have to have one. I'm saying mine's 17. Whenever I have a sports jersey, I would like it to be the number 17. Whatever. But there are numbers that are far more important to this world. And I'm about to show you what they are. So let's talk about this Fibonacci sequence. Fibonacci sequence. The Fibonacci sequence of numbers is 1, 1, 2, 3, 5, 8, 13. this sequence has a very particular rule as to how you find it. The basic rule comes down to, well, you start with a 1 and a 1. You have to start with a 1 and a 1. But then, in order to get the next number, you have to add up the two previous numbers. So you have to start with a 1 and a 1. In fact, you could even just start with a 1 and just say it's like 1 plus 0. And then you get 1. And then 1 and 1 make 2. And then 1 and 2 make 3. And then 2 and 3 make 5. 3 and 5 make 8. 5 and 8 make 13. And then you can go on with this and figure out basically an infinite number of numbers. In fact, ... just for the sake of argument, I'm just going to write down clearly not all of them, but just the next bunch of numbers. So the next number should have been 21, and then it would go 34, and then it would go 55, and then 89, and then 55 and 89 make 144, make 233, and then it keeps going forever and ever and ever. What is the huge deal? Why is this thing so important? Well, I'm going to show you that on a spreadsheet in a few moments. I'm going to create a little spreadsheet with this. But first, let me just kind of give you some notation here. First, I need you to write down these two things right here. Now, what I'm just indicating to you, this capital F is in reference to the Fibonacci sequence. And this little subscript, and yes, it is a little subscript, this subscript of 1 is basically saying, okay, the first number in the Fibonacci sequence. Well, the first number in the Fibonacci sequence is just a 1. Cool. Crazy. The next number. Well, what is the second term in the Fibonacci sequence? Well, it's a 1. Yay. Okay. It's a 1. Cool. Now, I could go on with this, but now I can make a general formula. And the general formula is this. For n greater than or equal to 3, f sub n equals f sub n minus 1 plus f sub n minus 2. This wacky notation is basically explaining how to calculate the Fibonacci sequence. And I'm going to be using this notation with a big thing that's going to be coming up in a few moments. But it's basically saying, well, any number, any term, the third term, the fifth term, the 10th term. Well, in fact, I'll write that out in red real quick, and I'll erase it right here. If I wanted the 10th term in the Fibonacci sequence, then, well, 10 minus 1, I would have to take the 9th term, 10 minus 2, and I would have to add the 8th term. And that just kind of goes back to that definition. You take the previous two terms, add them up, you get the next number in the Fibonacci sequence. That's all that this thing is really saying. But I am going to be using that notation. So now, what the heck it does. I'm going to show you something in Excel. Well, actually, should I do Excel or Google Sheet? I'll do Excel. You technically do either one. You know, I had a conversation with a class the other day about spreadsheets and Excel and Google Docs and all this other stuff. And it turns out, like, you guys are not taught how to properly use Excel spreadsheets. You don't know anything that it could do. The formulas that can go into it. But that's another day. That's another day. Check this out. Okay. Let me zoom in. Here we go. Get rid of that. There we go. So I'm in Excel. And I zoomed in so people could see it a little bit better, especially those people online. And this sequence starts with a 1 and a 1. That's just what it starts with. Let me actually just center everything here. Boop, there we go. I just centered everything. It starts with a 1 and a 1. You can see that in the top left corner. But now I'm going to do a little formula. Equals. Now this formula, I can program it to do whatever I want, but what I'm going to make it do is I'm going to click A1, and I'm going to add A2. What I'm basically doing is I'm just adding the previous two numbers. And you can see that it gives you a 2. There's that formula right up here where my mouse is circling. It just says A1 plus A2. But now here's the cool thing that Excel can do. And I don't know if you guys know how to do this. But you can actually bring the mouse to the corner of that cell, and it turns into a crosshair. And you can click and drag. And when you click and drag, it's going to replicate that formula. Watch what happens here. If I click and drag, boom, all of a sudden it gave me a 3. Now that 3, it's just replicating the formula. It's just dragging the formula down. I can do it again, gives me a 5. Do it again, gives me an 8. I can just keep doing it right here all the way down to 34. These are the numbers of the Fibonacci sequence. I could drag this thing down as far as I want. There you go, boom. I just got like 5-digit Fibonacci numbers right here. It's insane. Going back up here, there we go. But these are the numbers of the Fibonacci sequence. Absolutely insane. So you're telling me that in 6th grade, what teacher was it, by the way? 7th grade math teacher. And they just showed you this and they didn't show you what it could do? That makes me sad. Was it the end of the year? Did they do anything else with series and sequences besides Fibonacci? Okay. Watch what this thing can do now. There is a relationship where if you take any number within the Fibonacci sequence and divide it by the previous number equals this number divided by this number. Okay, it just gave you a 2. What's the big deal here? Let me type in the word ratio up here. Technically up here it's like a 1, but if I click and drag that thing, all of a sudden the numbers start changing. Let me go down a little bit farther, and let me show you what the heck is going on here. In fact, maybe I can freeze this. Hold on. View. I want to freeze those panels. Come on, I know how to freeze panels. I think it's under page layout. There was a way to freeze this. Oh, the formatting of this. There it is. Freeze panes, top row. There we go. Term, boom. There we go. So now it'll stay ratio and term at the top. Get rid of that. Oop, get rid of that. There we go. Bring it down, bring it down, bring it down. Boom. Okay. Look at this ratio right here. The ratio of dividing any Fibonacci term by its previous term. 2 divided by 1 gives you 2. 3 divided by 2 gives you 1.5. 5 divided by 3 gives you 1.6 repeating. And it just keeps going. But look what happens the farther I go down dividing these ratios. The number is ping-ponging. It's ping-ponging around a certain term. And it's settling somewhere very, very important. This is 89 divided by 55 right here. This is 144 divided by 89 right here. I'm going to keep scrolling down because Excel can help me with this. Let me bring it all the way down to here. Chapow. Now look at that number. Notice how it's not changing? Oh, yeah. It's changing a little bit, but not by that much. Let me go down a little farther. Yeah, now it's not changing by that much. Go down a little farther. Yep, it's definitely not going to change anymore. This ratio, 1.618. Seems like what the heck is the big deal? What is 1.618? 1.618 is the key to existence. 1.618 is everything in this world that we have today. Let me write something down in our notes, and I'm going to show you something here. And then I'm going to do a Google search and show you some stuff. So this is how you get any term in the sequence. That's how you get any term in the sequence, as I showed you before. Now, this is the messed up part. If you divide f sub n by f sub n minus 1, basically, if you divide a Fibonacci term by its previous term, if you divide those two, the result will grow closer to 1. Actually, I'll leave this up here. I'm going to get the exact decimal right here, just so I can write it down properly. Come on, you. Load properly for me. Come on, this thing. It's not going to give me the thing now. There it is. Cool. 1 point, can't see it. 61803398887 ... It'll keep going forever. If you divide those two, the result will grow closer to that decimal as n grows larger. That number, that decimal number, 1.618033, et cetera, et cetera, et cetera. This is the number phi, P-H-I. You know about pi. Pi is garbage. This number is more important. Oh, Mr. Murky, pi is the ratio of the circumference to the diameter of a circle. I understand that. This is more important. Why is it more important? Oh, I'm going to show you today. This is phi. They use the Greek letter phi. It looks like that. Looks like a circle with a line through it. I'm going to show you some stuff on Google Images in a few minutes. But this is the number that is approximately 1.618 ... This number, this ratio, is the most important number in the universe. This ratio can be found in the repeating patterns of sunflower seeds. This ratio can be found in the spirals of pineapples. This ratio can be found in the orientation of seeds within an apple. This ratio can be found in the way that petals grow out from the stem of a flower. It can be found in the spiral flying patterns of bees. It can be found in the reproduction rates of rabbits. It can be found in the spirals of your DNA. It can be found in the spirals of the literal galaxy that we are living in today. This ratio, this number, 1.618, is found within almost every, I'm not going to say almost, I'm going to say every living being in the history of the universe, that ratio is found. That ratio was known to the Greeks. That ratio was known to the Egyptians. They built it into their architecture. even to this day, this number is embedded in our brain as a number that is pleasing to the eye. This number is pleasing to the eye. Whenever you look at a TV, what ratio are TVs in nowadays? They're like widescreen, but it's not, if 4:3 is like full screen. Do you know what widescreen is? It's 16:9 or 16:10. The ratio is 16:10. When you look at a TV, it's like the ratio is 16:10 or something like that. It's like, oh, 16 divided by 10, 1.6. They're trying to replicate phi. When you look at pieces of paper, get my calculator here. Here we go. I'm going to do a little division right here. Boom. There we go. Well, pieces of paper, they're basically trying to replicate phi. Here, I'll show you something right here. I'll just do this little division right here. They were trying to replicate phi in an experiment where they showed people a bunch of different rectangles. They did this psychological experiment a long time ago. And in this, I'm trying to find my red one. There it is. In this psychological experiment, they showed people a bunch of rectangles where it was like, well, so this one's 1:1, and this one's like 2:1, and this one's like 8:5, and this one's like, I don't know, like 13:6 or some junk like that. I don't know. And they gave people choices of rectangles, and they said, pick the one that is most pleasing to the eye. And most people, probably about 40% of the people, picked that rectangle as being the most pleasing to the eye out of all the rest. And that was the one that closely resembled the ratio of phi. It is embedded in our DNA. Now, here's the thing. I can't do this experiment because I don't have enough people, but let me tell you a story. I can't do this experiment with you all because I don't have enough people. 2 years ago, when I was actually able to teach this with a full class, I had 20 kids in the class. Last year, I couldn't do it because we all went virtual in March, you know. But 2 years ago, when I was able to teach this lesson, I had 20 kids in the class, and I gave every kid, or I gave a couple groups of kids some rulers. And I had them, I'm going to draw this picture out for you. And I had them measure out the distance from their shoulder to their fingertip. And they wrote that down. And then they measured out the distance from their elbow to their fingertip, and they wrote that down. Then I collected all the data points from every kid in the class, and I put it in the calculator in a list. And I was able to show them, okay, here's the division of your arm length to your, elbow to fingertip length. And all these ratios were different. They were all different. Like one was like 1.7, one was 1.6, 1.4, 1.5. Like they were all different because people have different proportions. But when I averaged them all together, it ended up being 1.618. It was insane. There was a cheer that went up from the hills because they couldn't believe that the average of all human beings was this ratio known as phi. Do you guys know what the Vitruvian Man is? You'll recognize it if you see it. Watch this. Hold on. You'll recognize it if you see it. Vitruvian, I don't know if I spelled it right. Man. Oh, there it is. Boom. The Vitruvian Man. You ever seen this before? Yeah, there you go. Yeah. Da Vinci knew of this ratio. It's insane. Hold on. Phi in architecture. Check this out. It's going to show you some images here. Look at this. They built phi into the ratios of the Taj Mahal, into the Greek Parthenon, into the Cathedral of Notre Dame. This is the Parthenon again. I'm gonna not today, but I am gonna show you how to. Actually, no, I might do that today. Yeah, I might do it today. No, next time. Next time I'm going to show you how to construct that spiral, but that spiral is made using the ratios of phi. Da Vinci used it in the Mona Lisa. The Egyptians used it in the pyramid. There's that spiral happening on the Greek Parthenon. This is the Seattle Space Needle, I think. They created that little thing. What is that called? That area that people get in? I don't know if there's like a restaurant or something. Well, the ratio of where that restaurant is, if you take the bottom portion and divide it by the top portion, you get phi. It's pleasing to the eye. They have built it into almost everything. It's in the ratio of how they built the Eiffel Tower. I don't even know what that thing is. Look, it's in the ratio of the Last Supper. Clearly, they knew about this. And they realized that this calculation of phi, which I'm going to go into more detail of next time with all the definitions and stuff like that. I got more things to show you here. But they realized how important it was. Check this out. I'm going to show you a different list. That's phi in architecture. Check out this crap. Phi in nature. I mentioned that spiral. These spirals of this shell appear in the ratio of phi. Now, these are different spirals, but these are spirals of petals. These are spirals of a sunflower seed. That's a spiral in the bottom right there of a hurricane. These spirals show up in the ratio of phi. Look, you can, oh, that one you can't see that well, but maybe I can make this one bigger. Hold on. Open up in a new tab. Boom. There we go. There's the arm thing that I was telling you about, except they did the elbow to the wrist and the wrist to the fingertip. There's phi showing up in the rings of Saturn, in a butterfly's patterns where the little things occur, stuff like that. Oh, it's insane. I don't know if you've ever taken a photography class. On your phone, when you take a picture, do you get like the little grid sometimes? Yeah. The grid on your phone is based on a photography principle called the rule of thirds. It's called the rule of thirds. And if you actually Google the rule of thirds, you'll see why rule of thirds. You'll see why they do pictures like this. So here's the grid with like the rule of thirds. And the idea is that if you put your focus of the person not centered, but on one of these grid lines, it makes for a better picture. A little girl standing at the ocean, lots of ocean pictures, just kind of like centering that. It looks more visually appealing. And these photos, if there's the rule of thirds right there where the sun is. These photos, they use this rule of thirds to kind of make better pictures. Well, photographers have found that if they follow a different rule, they get better pictures. And it's not the rule of thirds, it's the rule of phi. If the ratio of those grid lines were not just immediately cut into thirds, but instead cut in such a way that resembled the ratio of phi, they actually get better visually appealing pictures. This number is embedded in our brain. This number, for some reason, is written on our souls. It is written into the DNA of the universe as something that we can recognize as appealing and recognize as beautiful. It is everywhere. Now, not today. I'm going to show you on Tuesday. I have you again. I'm actually going to take an apple. I got to remember to bring in a knife. But I'm going to take an apple and actually cut this thing open and show you that ratio of phi and how it actually applies to an apple. It's insane. Absolutely insane. It's the best visual representation I can kind of do for this thing. So let's go back temporarily to our notes right here. And let me show you a couple of examples of phi. Here we go. Where's my paper? Here's my paper. There we go. So the ratio of phi otherwise known as, well, which is approximately 1.618 to 1. It's approximate that. Is known as the, quote, golden ratio and the, quote, divine proportion, end quote. It is known as the golden ratio and the divine proportion. It is, they don't name pi that. They didn't give pi a special name. They just gave pi a dumb day. Hey, it's Pi Day. Pi Day is dumb. Phi is much more important, although I don't know how you do a Phi Day. It's like January 6th. It's like, that's kind of weird, I guess. I don't know, because I like the full number, you know. It could be January 6th, 2018, so we missed our opportunity. Gosh. But, yeah. But the names that they give this to show the importance of this. It's known as the golden ratio, the divine proportion. Like I said, I have a book on this. I left it at home. But this book has a lot of the pictures and images that I would have been that I showed you through Google searching it. Just to give you a small example. The average of all humans, arm length divided by the elbow to fingertip, or to fingers, I should say, is approximately phi. I'll write that phi symbol a little bit better. There we go. There we go. Cool. Now, mind you, it's if you take the average of all human beings. I'm sure you've met someone in your life, and I can tell you an example of this, that their proportions are a little bit off. Have you ever met someone where their arm lengths are actually just a little bit too short and they look like a T-Rex? Yeah. Clear. That's just an anomaly. That just happens. Not every human being is going to hit the ratio perfectly. But the average of all human beings hits that number phi. Let me go back over here. Phi in human face. Check this junk out. They say that if you have a human being whose face and head are more closely related to those ratios of phi, then that person is considered to be more attractive if their features hit those ratios. Now, you can't control whether or not your face ratios match phi. You can't really do that outside of plastic surgery, which is, I don't know, plastic surgery is weird. But like, clearly, look at this image right here. Open up in a new tab. This is a great example right here. Like, the guy on the left clearly is matching the ratios of phi. Now, the guy on the right, they clearly manipulated. They manipulated using like Photoshop and stuff like that. But if you ever saw like a guy like that on the right, you'd be like, holy crap, what the heck happened? It's not typical. It looks off-putting, makes people a little bit, you know, uneasy and nauseous. Look how low his ears are, you know? But I'm just saying that the closer that a person is to the ratios of phi, the more attractive they are to the general population. I say general population because obviously, you know, beauty is in the eye of the beholder, whatnot. But it's one of these like weird kind of arguments where they try to find people who have like these ratios, but they don't think about it. They don't think about how their bodies and their face relate to these ratios of phi. Look at these spirals. I'm going to show you on Tuesday how to create spirals like this in the ratio of phi. But you can see how that spiral, there's a mini spiral right on the ear. There's a larger spiral right here on the forehead where the hairline is. There's a spiral with where the way the lips are positioned, with the way the chin is positioned, with the way that the nose is positioned with the eyes. The closer that a human being is to the proportions of phi, the more attractive they appear to the general public. It's absolutely insane how this is embedded within our minds. in our brains, in our psychology, and you never think about it. You never think about the number phi at all. People just look at a person and they're like, oh, they're attractive, or no, they're not attractive, and they don't think about why. It's embedded in our brains. It really is. It's insane. Now, there's that pentagram right there. Hold on. Phi in pentagram. I'm going to be showing you this next week as to how that pentagram, not for devil worship, but for showing that number phi, hides all of these ratios. It's absolutely insane. There's the spiral drawn on it right there. In fact, when people see the pentagram, they do think like upside down pentagram. They think like devil worship or some junk like that. But in reality, like ancient pagans used symbols like this not to represent the devil, but to represent that ratio of phi. It's absolutely insane. Huh. It's just one of those things. I love it so much. But it shows up in so many different things. I'll tap phi in pyramids. I showed you a little bit of this, but I wanted to show you a little bit more. I'm not even kidding you. They built the pyramids of Giza in the proportions of phi. Like, absolutely insane. I don't know if you've ever heard stories of the pyramids of Giza and how they built them, but they built them so stinking precisely. They built them like 4,000 years ago or 5,000. I don't even know how many thousands of years ago. Absolutely insane. But they built them with such precision, absolute precision, that they have this ratio of phi embedded in them. Because they realized, wow, this number is important. This ratio is appealing. Absolutely insane. So, just a couple of things here. The ratio phi. The ratio phi is embedded in nature, in art, in architecture. I can spell architecture. Architecture. I do not know how to spell architecture. Hold on. Now I got to look it up. Yeah, was I spelling it right? Oh, no, I was. Yeah, I was spelling it right. Look at me. Arch-I-texture. I doubted myself. But that's exactly how you spell it. In architecture. In human psychology. Yeah, in the very universe we are in. Like, it's absolutely insane to think that these ratio of phi, these spirals, yes, these ratios govern the spirals of the very universe that we are in right now, all the way down to the DNA that is in your body, on the macro scale to the micro scale. This phi, this ratio, it is absolutely insane. See, this is what I'm saying. You said your teacher showed you in middle school. And I'm like, how did your teacher not show you all of the different things that it applies to? It's insane. But that's the way that it works. The craziest thing to see it, the craziest place to see it, I think, hold on, get this thing up here. There we go. Is it in a pineapple? Hold on. Phi pineapple. No. Oh gosh, they're thinking I want to do like college stuff. Hold on. Phi in pineapple? Nope. Number phi. Nope. Ratio. Okay, good. Here we go. I'll open this one up. Open image in a new tab. See, the coolest thing is with a pineapple, in my opinion, Because with a pineapple, like if you've ever, like, I don't like pineapple. I don't like the taste of pineapple. I don't know if you do or not. Take it or leave it, but you've seen them, right? But the way that these pineapples work, you can see a lot of different things here. Like, you know, they say the flowers often have 3, 5, 8, or 13 petals. 3, 5, 8, 13. Those are all numbers in the Fibonacci sequence, first of all. But then you can see the way that these spirals are working out. You can see there's spirals going in a lot of different directions. These spirals can go in kind of like a curvy vertical direction or in a horizontal direction. This horizontal has a spiral of 5. This one has like a spiral of 8. This one has a spiral of 13. Absolutely insane. Absolutely insane. This is actually an apple. I don't know why they threw the apple in there. But then you can see right here. Now, this is the craziest part. I told you about the petals on flower. Do you know why? Holy crap. If the petals grow out in a spiral in the ratio of phi, they will maximize the amount of sunlight that will hit each petal. It will maximize it. It is the most optimal way for petals to grow on a flower in order for them to react to the sun. Insane. Absolutely stinking insane. I took a picture. See if I can find this thing. When we were quarantined last year, it was in between classes, and I took a picture of something. It should still be in my Google Photos. April 2020. Yeah, it should be here somewhere. There's my daughter's birthday. Oh, there it is. Found it. Boom. Oh, you can't see it. So I had my daughter. She picked this for me. And I looked at it, and I'm like, oh, holy crap. Let's move over a little bit. There we go. Hold on. There we go. Get that thing out of the way. How do I get this thing out of the way? Boom. There we go. That's good. But it was just literally like a flower. It was just a flower that, and I'm just looking at it. I'm like, this flower is perfection. This flower is absolute perfection. It's a little difficult to see, but it was a bit focused on the picture itself. But the spirals of these, like, I don't even know what these are, like pollen? I don't know what the heck this is on the flower. Yeah. But they grow in the spiral ratio of phi. Oh my gosh. It's perfection. It's absolute perfection. That's insane. But yeah, that was a picture we took last year. See if I can get out of that. Zoom. There we go. Not to there. There we go. Fibonacci. Oh my gosh. Seriously, just scratching the surface. There are hundreds and thousands of different things that apply to this ratio. It's absolutely insane. So, next time, we are going to dive a little bit deeper. I'm going to remember to bring in that book because I have some things to show you in that book. And we have some investigations to do with this number of phi because it is such a stinking huge topic. It's absolutely insane. I love it so much. Okay. The time is approximately 8:15. Class goes till 8:43. As I said at the beginning of class, for those of you that are here and for those of you that are online, I wanted to give you some time to work on that project that I assigned on Wednesday. That project is not due until Monday. It is not due until Monday. But just to kind of recap some of the details here. If you go to Google Classroom and you open up the thing that says 4-color project /absent day. I said absent day because I clearly wasn't here that day. But there is a link to a Quora question about real-life applications of the 4-color theorem. Your task, I'm just going to read this. Your task is to research real-life applications of the 4-color theorem that are not about coloring maps. According to this link, and you can see the link yourself when you click on it, the question has been somewhat answered with a few examples. What I want you to do is I want you to scour the internet for several applications of the theorem that are not about coloring maps, find more than just the ones mentioned in the link. Then I want you to research 2 of the examples in greater detail. You pick whichever 2 is most interesting to you. I want an explanation and an example as to how it works. You can do this in Google Slides. You can do this in Google Docs. But basically, I want you to show how the four-color theorem applies to those ideas and an example as to how it would work. This is not meant to be a crazy large-scale project. This is really not. This is really not meant to be like a huge thing. In fact, like I said, I'm giving you a block of time right now during class to kind of get a lot of it done. Beyond that research, there is also the little challenge thing, which I do have extra copies over here. For those of you that are online, obviously, I can't physically hand you this copy. There we go. Just in case there are 3 in there. It's like if you mess up or something, you know? Because it's always a possibility. And if you're using markers or colored pencils or crayons, and it's like, how do you erase that, you know? Yep. There we go. But so on Wednesday, obviously you weren't here, I left the copies and I left the colored pencils to kind of knock that part of it out, you know. For those of you that are online, obviously, you know, if you can't print it out, there are ways of doing it through like, Microsoft Paint or some other website that you can like color things on. But if you can print it out, then it's just a little fun coloring game, I guess, so to speak. But yes, so this is your task. Like I said, I wanted to give you roughly 20-ish minutes. Right now would be exactly 24 minutes to take this remaining time and to continue or start for those who maybe, you know, didn't check in. Oh, no, you did. Y'all did check in on Wednesday. You did. Yeah, anyway, whatever. But this would be an opportunity to get that thing moving. So I'm going to leave the live chat open. And if you do have any questions, I'm going to be able to see it on the chat. But yeah, we have until 8:43. So let's get this thing rolling. Woo! There we go. Nicole, you missed a picture. I'll bring it back up here. So I was teaching this class last year. April? Yeah. I was teaching this class last year, and my daughter, which by the way, look at her sleeping on that cat, just saying. But my daughter was in the garden, there it is, and she found this, and I just thought that was perfection. But that's the ratio of 5. Those are the spirals of 5 embedded within this flower. I just thought it was awesome. So I took a picture of that. I uploaded it to the Google Drive for my kids. I should get off of 90% of my pictures are my kids, just so you know. But let's see here. Boom. Oh yeah, but yeah, you came in at the tail end of that. I'm giving people the opportunity to work on the projects. Uh-huh. Oh, these are cool pictures. Still not us. know I'm taking a huge risk, but I'm going to go fill up my water bottle. Clearly, this is a huge risk. Oh, I meant leaving you guys alone. Whatever. Shut up, me. bell's going to ring in approximately 1 minute. I'm going to sign off, and I will see all of you people on Tuesday. So, yeah, cool.